See this problem. A circular coil of 20 turns and radius 10 centimeters is placed in a uniform magnetic field of 0.1 Tesla normal to the plane of the coil. If the current in the coil is 5 amperes, what is the total torque on the coil and total force on the coil and average force on each electron in the coil due to the magnetic field? The coil is made of copper wire of cross-sectional area 10 to the power of minus 5 meter square, and the free electron density in copper is given to be about 10 to the power of 29 per meter cube. Our motive is, so given that there is a circular coil having some n turns which is having some radius r and some current is flowing in the copper wire, so this is kept in a uniform magnetic field B, and it is kept like the plane of this coil is normal to the field. So in that case, if you draw a normal to this plane of the coil, that normal will make 0 degrees with the magnetic field. This normal vector can be considered as aerial vector A. So the angle between this A and B is 0. So in this case, we need to find out that torque acting on the coil and the force acting on the coil and average force acting on each electron. These three we need to find out. That is our motive. Now come to the investigation part. Circular coil has 20 turns, so capital N is equal to 20 turns, and the radius R is equal to 10 centimeters for that coil. Using this, I can find the area of the coil, which can be considered as aerial vector magnitude, and the uniform magnetic field B is equal to 0.1 Tesla, and the current flowing in that coil I is equal to 5 amperes, and two more values are given, that is cross-sectional area of that copper wire, that is A is equal to 10 to the power of minus 5 meter square, and as well as the electron density in that copper wire, that is N is equal to 10 to the power of 29 per meter cube. These are the given quantities. Now I want to resolve the problem. So we already know that the torque acting on a coil which is placed in a uniform magnetic field, tau is equal to NIAB sin theta. N is the number of turns in the coil, I is the current flowing in that coil, A is the area of the coil, so in our case it is AC, B is the uniform magnetic field, and theta is the angle between that normal vector and the uniform magnetic field. So in this case theta is 0, so we will get torque as 0 Newton meter. And now the force. So torque can be defined as R cross F. R should not be 0, so if tau is 0, F will become 0. That implies the force acting on that coil F is equal to 0 newtons. Now come to the average force on each electron. For this we need to consider the core properties of that copper wire. So electrons are there which are moving with some velocity. Here we can consider this velocity as a drift velocity. So an electron is moving with drift velocity in a uniform field, then we can find the force acting on that electron. So which can be represented as F is equal to BQE is the force acting on the charge Q having velocity V when it is moving in a magnetic field B. So in our case it is FE is equal to B into E into VD. VD is the drift velocity of that electron. Now drift velocity can be written as Fe is equal to BE into I by NE into A. I is the current flowing in that copper wire, N is the free electron density in the copper wire, and E is the charge of each electron, and A is the cross-sectional area of that copper wire. E gets cancelled, so the remaining thing is B into I divided by N into A. Now I want to substitute the values. B is equal to 0.1, I is equal to 5 divided by 10 to the power of 29 into A is 10 to the power of minus 5. So 10 to the power of minus 5, 10 to the power of 29. So you'll get 10 to the power of 24. If it goes up, it will become 10 to the power of minus 24, and by adding with this 0.1, you will get 5 into 10 to the power of minus 25 newtons. So this is the average force acting on each electron when it is moving in the coil.